In the high-stakes world of aviation, where every second counts and every decision could mean the difference between life and death, pilots are constantly honing their skills through rigorous training. But sometimes, as we'll see in this story, what seems like preparation can actually sow the seeds of disaster. Imagine, if you will, playing a game of Tetris. The blocks are stacking higher and higher, faster and faster, and you find yourself reacting, not thinking. You know what's coming next. It's game over. But in aviation, this is not just a game. It's life or death. And for these two pilots, the stakes could not have been higher. As they fought to regain control of their aircraft, the more they did, the worse it became. Let's take a closer look at what happened. When a new pilot takes their seat in the cockpit for their very first revenue flight, they're expected to perform at the highest level, just like the captain beside them. But here's the catch. While they're fully qualified to operate the aircraft, their real learning happens in the simulators, which are supposed to replicate every condition they might face in the air. This is where the story begins. The pilots involved in today's incident had been flying for Air Transat, a Canadian long-haul airline, since the late 90s. They'd started their careers on the Lockheed L-1011 TriStar and eventually transitioned to the Airbus A310, with each pilot spending several years training in simulators to master the aircraft. But even with the most intense training, it wasn't enough to prepare them for what was about to happen. The Airbus A310 simulator they trained on was supposed to replicate the actual aircraft with great precision. But there was a major flaw. The simulator was configured to mimic the A310-221 model, which had less powerful engines than the A310-308 used by Air Transat. This discrepancy meant that the pilot's training was based on an aircraft that was less capable than the one they would actually fly. They thought they understood how the real A310 should perform, but in reality, their perception was warped. This leads us to a critical point of failure. The simulator also failed to accurately replicate the control forces that pilots experience during flight. On smaller aircraft, the control columns are directly connected to the flight control surfaces, meaning that pilots feel the aerodynamic forces as they fly. The harder they pull the control column, the more resistance they feel, making it hard to over-control the aircraft. But on larger airliners like the A310, there's no direct connection between the control column and the flight controls. Instead, a device called the Feedback and Limitation Computer simulates the feedback by calculating the required force based on factors like airspeed and the position of the control surfaces. This system is designed to help pilots feel how the aircraft is behaving in real time. It's especially critical for understanding how to adjust the stabilizer trim, which controls the pitch of the aircraft. When the stabilizer is out of trim, pilots need to apply more force to maintain control, a signal that the aircraft isn't properly set up for its current flight phase. But the simulator in use by Air Transat didn't replicate this phenomenon accurately. The pilots in training were able to override the feedback from the stabilizer, even at speeds well above 250 knots, which led to what's known in aviation as negative training. They learned how to push the aircraft beyond its limits without feeling the true consequences. This lack of realistic feedback in the simulator left them ill-prepared for the real-world challenges they would face when they encountered this issue during a flight. As we'll see, this mismatch between training and reality would have devastating consequences. Let's draw a comparison to a similar real-world incident: the 1996 crash of a Boeing 757 operated by American Airlines. The pilots, who had experienced significant turbulence, made several adjustments to the trim and failed to recognize when the aircraft was out of balance. Despite the advanced technology and systems in place, their inability to adapt quickly enough led to a tragic outcome. The same could have been true for these Air Transat pilots had they encountered similar conditions. As we continue, we'll delve deeper into the technical specifications and understand how these flaws in training contributed to the crisis that unfolded. But for now, it's clear. The combination of negative training, simulator discrepancies, and the failure to truly understand the aircraft's performance created a deadly situation that could have been avoided with proper preparation. Training is a critical element in aviation, and it can be the difference between success and disaster. However, as we learned from this incident, training only remains effective if it is accurate and mirrors the realities pilots will face in actual flight. Inaccurate training can cause pilots to react incorrectly when the pressure is on, which is exactly what happened here. On March 5, 2008, at Quebec International Airport in Quebec City, Canada, the stage was set for what would become a fateful flight for Air Transat Flight 211. The pilots had already completed a long transatlantic journey from Paris, and now they were preparing for a relatively short hop to Montreal. But what seemed like a routine flight was anything but, especially for the captain. This particular flight was not only a regular trip, it was also a check flight. The captain, who had been flying as a first officer on the A310 since 2004, had recently upgraded to captain after completing proficiency checks in both the simulator and actual line training. At the time of this incident, however, the captain had less than 100 hours flying the A310 as the pilot in command. The flight was especially important because the captain was being evaluated for his extended twin-engine operations, ETOPS, rating, a qualification that allows pilots to fly long-haul flights over areas where they cannot reach an alternate airport within a specific time frame. The captain's evaluator, a highly experienced instructor with years of flying and instructing on the Airbus A310, was accompanying him. But even a seasoned instructor can feel the pressure when conducting an evaluation, which automatically raises the stakes and increases workload, especially for the captain. When pilots know they're being watched and evaluated, there's a natural tendency to second-guess themselves, trying to operate perfectly. Ironically, this often leads to more mistakes, as pilots become focused on trying to prove themselves, rather than reacting instinctively to the situation at hand. In this case, the stress was further compounded by external factors that made the flight trickier than usual. First and foremost, the weather conditions were far from ideal. Winter in Quebec City brought drifting and blowing snow, which reduced visibility to just 400 meters at times, far from ideal for an operation in such conditions. The wind was strong, blowing from the east at 24 knots, with gusts reaching up to 36 knots. These conditions created a hazardous runway surface, with patches of hard-packed snow mixed with areas of clear pavement, and snow drifts up to 2.5 centimeters deep. But it wasn't just the snow and wind that posed a challenge. It was the runway visual range, RVR, a critical measurement of visibility used by pilots to determine whether it's safe to take off or land. The RVR on this day was reported at 1,800 meters, which was within the permissible range for most Air Transat crews, as they were typically cleared for takeoff with an RVR of at least 1,200 meters. However, due to the captain's limited experience as a pilot in command, with fewer than 100 hours, he was restricted to operating with a minimum RVR of 2,600 meters. On the other hand, the instructor, with much more experience, was rated for a lower RVR of 600 meters or above. Despite the weather and visibility limitations, the crew concluded that with an RVR of 1,800 meters, they would be able to take off safely. But here's where we need to understand how technical data intersects with real-world decisions. The RVR value is an incredibly important measure, yet it can often be misunderstood or incorrectly assessed, especially under pressure. The captain and instructor, both assuming that the flight could proceed, didn't fully take into account the limitations of the RVR rules based on the captain's experience level. This decision, which on the surface might seem reasonable, is an example of how small, seemingly inconsequential factors can compound into a dangerous situation. When it comes to flight safety, there is no room for assumption or complacency. The key takeaway here is the importance of understanding every variable at play: the weather, the visibility, the aircraft's condition, and of course the pilot's limitations and experience. Similar incidents have occurred in aviation history, where overconfidence and inadequate assessment of conditions led to disasters. One such example is the 1990 crash of a DC-10 in Sioux City, Iowa. In that incident, a series of miscalculations and misjudgments by the crew, compounded by severe weather, led to a loss of control. Despite the technology at their disposal, the pilots were caught off guard by conditions they hadn't fully anticipated. Much like the Air Transat crew, they had to rely on their training and judgment, but their judgment was clouded by the stress of the situation. As we continue, we'll explore how the events unfolded and how the failure to account for all technical variables contributed to what would ultimately become a critical emergency. Understanding the context of this flight, the stress of evaluation, and the pilot's inexperience reveals just how easily things can go wrong when every factor isn't fully understood and accounted for. The situation was unfolding in a way that seemed manageable, but there were numerous signs that this flight wasn't going to be as straightforward as the pilots thought. The crew had calculated their takeoff parameters, but the reality was that they had taken shortcuts and hadn't fully prepared for the unexpected consequences. As I mentioned earlier, training only works when it's accurate, and the pilots in this case had been trained on a simulator that didn't fully replicate the performance of the actual aircraft. This wasn't just a minor discrepancy. It was a critical difference, especially when it came to handling power and performance during takeoff. Let's dive deeper into what went wrong, beginning with the pre-flight calculations. The pilots needed to account for the runway condition, which was contaminated with snow, ice, and water. Typically, this would require very precise calculations for the takeoff speeds, like V1, the decision speed, and VR, rotation speed. Under normal circumstances, these values are determined based on a set of variables: aircraft weight, outside temperature, pressure, and runway conditions. However, when faced with a contaminated runway, these calculations become more complicated. The pilots knew the runway was contaminated, but instead of doing the required, more meticulous calculations, they opted for a shortcut. They used the V speeds for a wet runway, which would be quicker but not entirely accurate. While the difference might seem minor, it was enough to put the crew at risk. In fact, when the runway is contaminated and a rejected takeoff occurs, the aircraft may not have enough stopping distance, which could be catastrophic. Now, let's look at another critical factor: takeoff thrust. Air Transat's procedures called for the use of maximum thrust, TOGA, when taking off from a contaminated runway. While this increases performance and reduces the risk of poor acceleration, it comes with a price. Maximum thrust puts more stress on the engines, increases fuel consumption, and results in more noise. On top of that, with a lighter than usual aircraft due to fewer passengers and less fuel, the pilots were about to experience an incredible level of thrust. The combination of a light aircraft and maximum thrust meant the A310 would be far more responsive than what the pilots were used to. This is where their simulator training had left them ill-prepared. The simulator they had trained on had engines with lower thrust than the real A310s, which meant that when they experienced the real power on takeoff, it likely took them by surprise. The captain had not been fully briefed or prepared for this level of performance. The result was that they had underestimated how quickly the aircraft would accelerate and how it would behave during takeoff. Another crucial factor in the pre-flight calculations was the stabilizer trim setting. The stabilizer trim ensures the aircraft is balanced during takeoff, preventing it from being nose-heavy or nose-light. The pilots had set it to 1.9 degrees nose-up, which was appropriate for a lighter aircraft, but not ideal. The stabilizer trim is a fine-tuned adjustment, and any mistakes can have significant consequences during rotation. In this case, the setting was closer to a full nose-down position, -3 degrees, which could have resulted in a more challenging takeoff. Once these pre-flight calculations and settings were made, The crew requested pushback and began their taxi to runway 06. It wasn't long before the air traffic control tower issued a modified clearance. In order to maintain safe spacing between the departing aircraft, they were asked to make a right turn onto heading 110 degrees and level off at 3,000 feet before handing over the flight to the Quebec City terminal controller. This slight modification to their departure route, while seemingly minor, would add another layer of complexity to the flight. The crew was already under stress, juggling pre-flight calculations, the weight of the evaluation, and the demanding weather conditions. And now, this new instruction to change their course would add even more mental load to the already tense situation. This combination of factors, rushed calculations, unpreparedness for the aircraft's real performance, a tricky runway, and the unexpected stress of the modified clearance, set the stage for what was to come. As we've seen before in aviation history, such missteps can lead to critical failures. The question now was whether the crew could recover from these compounded challenges, or whether this flight would turn into yet another example of how small decisions can lead to catastrophic outcomes. To highlight a similar situation, we could look at the 2000 crash of Alaska Airlines Flight 261, which experienced a series of mechanical failures that were exacerbated by crew miscommunications and poor training. The crew, under immense pressure, made errors that contributed to a disaster, similar to how the pilots here were now battling a series of small oversights that could snowball into a much larger problem. As we continue, we'll explore how the crew's decisions, based on faulty training and incomplete preparation, led them down a dangerous path. The next steps would be critical in determining if they could regain control of the situation, or if they would fall victim to the very mistakes that had been building since their first flight in the A310 simulator. As the aircraft surged down the runway, something was clearly wrong, but the situation had already escalated to a point where everything was happening too quickly for the pilots to react with the calmness and precision that was required. Let's break this down, starting with the climb procedure. Typically, during a standard climb out, pilots rely on the Flight Management System, FMS, to manage the autopilot, throttle, and climb profile automatically. The system guides the aircraft's ascent to the desired altitude, adjusting speed, rate of climb, and angle of climb. This provides a much-needed simplification during a busy phase of flight. However, in this case, the situation required a different approach. Because of the low altitude level-off procedure that had been prescribed due to the modified departure clearance, the pilots needed to switch to the Speed Reference System, SRS, mode. This mode changes the way the autopilot works. It no longer manages the climb profile automatically, but instead modifies the aircraft's pitch to maintain the selected airspeed. The manual intervention of the pilots was required for adjusting throttle settings at certain points, such as at 2,500 feet, when the power needs to be reduced from takeoff thrust to climb thrust. This was a more hands-on approach, one that required the crew to be alert and ready for the challenges of a low-altitude flight profile. Additionally, the takeoff procedure itself should have followed a well-defined series of steps, calling for positive rate of climb, retracting the gear after verifying the climb was successful, engaging the autopilot, and making sure the autopilot was correctly set for climb thrust when reaching 2,500 feet. However, these standard procedures were soon disrupted by a seemingly small but critical issue: the instructor's headset. Just as the aircraft accelerated down the runway, preparing to rotate, the instructor's headset became partially unplugged. This momentary malfunction caused a loud and jarring squeal in his ears, momentarily disorienting him. In the ensuing panic, he fumbled to reconnect his headset, but realized too late that he had missed calling the critical rotate command, the signal for the captain to initiate the aircraft's rotation into climb. At this point, the captain should have recognized that the rotation had not been called as they accelerated through VR, the critical rotation speed. He was the pilot in command, and the responsibility to initiate rotation rested with him. However, There were numerous factors that made this moment even more fraught. This was the captain's first low-visibility takeoff, as pilot in command on the Airbus A310. And with strong gusty winds and limited visibility, he was likely focusing more on keeping the aircraft aligned with the runway centerline than on the details of the rotation. By the time the instructor frantically called out, "Rotate," 5 seconds had passed, and the aircraft had already reached 182 knots, 44 knots above the VR speed. With the aircraft already accelerating so rapidly, combined with the light weight of the aircraft and the full thrust setting, it became an uncontrollable situation. The captain, now fully aware of the problem, tried to pull back on the control column, but the aircraft's rapid acceleration meant it became airborne almost immediately. The force of the climb, combined with the high speed and light load, left the captain in a difficult position. He quickly realized that they were about to exceed the flap and slat limitations for the 15-degree configuration, an important aspect of the aircraft's performance. The combination of these factors, failure to rotate on time, miscommunication, and the aircraft's excessive speed, now posed a serious risk to the safety of the flight. This scenario is not without its parallels in aviation history. Consider the 2009 crash of Air France Flight 447, where a combination of miscommunication, technical failures, and pilot confusion led to a tragic outcome. In both cases, errors in basic flight procedure, compounded by external stress and miscommunication, led to a dangerous situation. The captain, despite his qualifications, was placed under immense pressure, which resulted in lapses in judgment at a critical moment. In this case, the chain of events set in motion by the failure to call, rotate properly, and the lack of immediate corrective action resulted in a scenario where, despite being in control of the aircraft, the crew was now struggling to regain that control. The technical failure of the headset was a freak accident, but the human response, slow recognition of the issue, followed by delayed action, set the stage for an aircraft that was now dangerously close to exceeding its operational limits. This moment, marked by a critical lapse in timing and communication, highlights just how quickly things can unravel in aviation when a series of small mistakes compound. As we continue, we'll see how these errors, in combination with the previous training deficiencies, contributed to a flight that was spiraling out of control. At this critical moment, the chaos in the cockpit was palpable. The captain, now fully in control of the aircraft, was manually flying the plane and attempting to follow the flight director's commands. However, the situation had become increasingly difficult to manage, and the stress was evident. The flight director was instructing the captain to pitch up steeply to regain the proper climb speed, but at the same time, it was also guiding him to initiate a turn to 110 degrees, a heading that had been preset before takeoff. Under normal circumstances, the pilots would have been expected to wait until they reached 400 feet before making any turns. However, in the heat of the moment, the captain likely became tunnel-visioned on the flight director's guidance, and at only 40 feet above the ground, he began the turn to the right, pushing the nose of the aircraft up steeply. As the captain raised the nose and started banking right, he realized that in order to hold the climb speed, he would need to pitch the aircraft up beyond 20 degrees, which was the maximum pitch angle typically used during normal operations. This was a crucial moment. If he didn't pitch up further, the aircraft could exceed the flap limitation speed, but if he pushed the nose up too much, it would be harder to meet the altitude level-off requirement of 3,000 feet that had been cleared by air traffic control. The captain was now stuck in a dilemma, caught between the need to follow the flight director's instructions and the limitations of the aircraft's configuration. In addition, there was confusion about a fundamental procedural call. The instructor had forgotten to call positive climb after liftoff, and the captain, perhaps distracted by everything going on, also forgot to call gear up. The gear remained down, the flaps were still extended, and the engines were still at full takeoff thrust, which was putting the aircraft into a dangerously unstable situation. At this point, The aircraft was climbing at an extraordinary rate of 6,300 feet per minute, with an airspeed of 213 knots. The gear was still extended, and the thrust remained at toga, the maximum takeoff thrust. All of this combined to create a scenario that was far from stable, and as the aircraft approached 3,000 feet, the need to level off became even more urgent. In fact, they were just seconds away from overshooting 3,000 feet. After 22 seconds, the captain finally called for the autopilot to be engaged, and the instructor complied. The autopilot was now engaged, and the aircraft began to pitch forward to level off at 3,000 feet. However, the captain's decision to retract the flaps at 1,700 feet, a full 1,300 feet earlier than the prescribed 3,000 feet, added another layer of complexity to the situation. While the instructor attempted to retract the flaps, he left the slats extended, which further compromised the aircraft's performance. As if this wasn't enough, the instructor also realized that the landing gear had still not been retracted, and he quickly took action to retract it, which further reduced drag. However, in the midst of all this, neither pilot had realized that the critical step of reducing thrust at 1,500 feet, in accordance with the low-altitude level-off procedure, had been completely forgotten. This failure meant that the engines were still producing full takeoff thrust, putting even more stress on the aircraft and increasing the risk of instability. What followed was a cascade of errors that only exacerbated the situation. 5 seconds after the autopilot was engaged, the captain realized that the aircraft would not be able to level off at 3,000 feet from such a rapid climb. In a panic, he disengaged the autopilot, triggering a loud and persistent autopilot disconnect alarm that would continue throughout the ensuing moments of crisis. Despite this alarming sound, the captain didn't immediately correct the issue by pressing the autopilot disconnect button again. The overwhelming nature of the situation had clearly taken its toll on him. At this point, only 27 seconds had passed since the aircraft had rotated, but in that short time, the situation had spiraled out of control. To make matters worse, the instructor, who was supposed to be helping guide the captain through the stressful moments, was not actively assisting. In my own experience, when conducting line checks as an instructor, it's crucial to remain calm, organized, and proactive, especially when things start to go wrong. The instructor needs to be an active participant in managing the situation, helping the captain make the right decisions and staying calm under pressure. However, in this case, it seems that the rapid escalation of events overwhelmed both pilots. By the time the aircraft climbed through 2,400 feet, with a vertical speed of over 5,000 feet per minute, the captain began to push the nose forward in an attempt to level off. However, the aircraft, in its current configuration, was still climbing rapidly, making it difficult to control the situation. This moment highlights the peril of compounded errors. Each small mistake, from the instructor's headset issue to the failure to follow proper procedures, added up to a deadly mix of confusion and instability. It was a situation where the pilot's training, preparation, and decision-making all played a part in escalating a manageable situation into an emergency. The chain of events had set the stage for what was about to unfold, and the pilots were now in a race against time to regain control before things went further off course. At this critical juncture, the captain was struggling to maintain control of the aircraft. The sheer force on the control wheel was becoming overwhelming, and instinctively, he reached for the electric trim switches on the yoke. The purpose of trim is to relieve the pilot from the constant physical force required to maintain control of the aircraft, and trimming nose down seemed like a natural response to the heavy forces he was feeling. However, this seemingly simple action set off a chain reaction that would escalate the situation even further. The issue began when the captain attempted to relieve the control forces by trimming nose down for 3 seconds. Unbeknownst to him, during the 5 seconds when the autopilot had been engaged, the aircraft had already begun trimming nose down as it attempted to capture the selected altitude. So, when the captain activated the trim again, it was an uncoordinated move that pushed the trim all the way to the electronic nose-down stop, approximately 2.7 degrees. Now, it's important to note that trim should be used after achieving the desired flight attitude, not while trying to control the aircraft's movements. If you start trimming before achieving the correct attitude, you run the risk of over-trimming, as the pilot cannot accurately judge the exact amount of trim needed. This is exactly what happened here, and it played a significant role in the aircraft's subsequent rapid pitch reversal. As the trim was adjusted improperly, the aircraft transitioned from a steep climb to an uncontrollable descent. Within a matter of seconds, the plane had climbed to a maximum altitude of 3,100 feet, only to drop into a 2,000 feet per minute descent. This transition occurred in just 7 seconds, which is an incredibly short time frame, leaving the captain with almost no opportunity to react. The aircraft, now in a terrifying descent, was still under full takeoff thrust, with the stabilizer trim set fully nose down. The airspeed increased rapidly as the aircraft descended, climbing from around 200 knots to more than 240 knots in a matter of seconds. This rapid descent and acceleration would have been highly disorienting for the captain, especially as they were now in the clouds and had no visual reference outside the cockpit. This is where the captain may have experienced what is known as the somatogravic illusion, a phenomenon where the human vestibular system misinterprets acceleration as a pitch-up. Essentially, the pilot's inner ear, which senses acceleration and pitch changes in similar ways, could have made the captain feel as though the aircraft was pitching up, even though it was actually pitching down. Pilots are trained to ignore these kinds of illusions and rely on their instruments, but in a high-stress environment, such as this one, the captain's focus likely wavered. In the heat of the moment, he may have believed that the aircraft was pitching up and reacted by making small control inputs to correct it. This perception could have made him hesitant to pitch the nose down further exacerbating the problem as the aircraft continued to descend rapidly. As the situation worsened, the captain, in an attempt to correct the descent, began reducing thrust. Unfortunately, due to the configuration of the Airbus A310, specifically the undermounted engines, the reduction in thrust actually made the nose-down tendency even stronger. This is a key design feature of aircraft with low-mounted engines, where reducing thrust can accentuate the aircraft's natural tendency to pitch down. In his efforts to correct the thrust, the captain accidentally bumped the toga levers, which are used to initiate a go-around procedure during an approach. The go-around mode was now triggered, causing the aircraft to revert to full takeoff thrust, and the slats began to retract. This further increased the speed, compounding the already unstable situation. Amid all of this confusion, the captain, still perceiving a pitch-up situation, failed to recognize the actual cause of the increasing airspeed. With his situational awareness severely degraded, the captain likely started to question whether they were experiencing an unreliable airspeed malfunction, an issue he had just reviewed in his training. But despite the correct speed indications from the instruments, his overwhelming stress and confusion led him to misinterpret the data. Had the captain applied the appropriate procedure for unreliable airspeed, such as assuming a known pitch attitude and thrust setting to ensure a stable climb, the situation might have been recoverable. However, in his overwhelmed state, the captain did not take this crucial step. This tragic series of errors highlights how the combination of poor situational awareness, over-reliance on instinct, and stress can quickly derail a situation, even when the aircraft's systems and instruments are functioning correctly. This is a stark reminder of how critical it is for pilots to remain calm and stick to well-established procedures, especially under pressure, and how even minor missteps can snowball into a much more dangerous situation. The aircraft's rapid acceleration, descent, and increase in speed created a deadly scenario, one that could have been avoided had the captain followed the proper protocols and maintained control over his actions. As the situation continued to spiral, the instructor realized the plane was pitching down rapidly, But the captain, now deeply overwhelmed by the workload and stress, wasn't making any corrective inputs. In a last-ditch effort to draw the captain's attention, the instructor called out, "Hey, you're pitching down!" When there was no response, he repeated his call. But once again, the captain failed to respond. This lack of communication likely wasn't due to disobedience, but because the captain was so task-saturated that he literally couldn't hear the calls. The brain, under extreme stress, tends to filter out unnecessary stimuli to focus on what it perceives as most important, which could explain why the captain didn't register the instructor's calls. In situations like this, where a pilot fails to respond to 2 consecutive calls, Air Transat had a procedure in place called the 2-call rule. According to this procedure, if the pilot flying doesn't respond, the pilot monitoring must take control of the aircraft. So, the instructor took over control, announcing, "I have control," and immediately assumed the role of pilot flying. This was absolutely the right thing to do, considering that the captain had lost situational awareness and was no longer able to keep the aircraft on a stable flight path. But despite this transfer of control, the situation was far from over. The instructor now found himself in a much worse position, as he didn't have the full picture of what had been happening in the cockpit. The captain hadn't communicated the crucial detail that he had been trimming the aircraft's nose down. Without this knowledge, the instructor had no way of knowing that the aircraft was already trimmed fully nose down, as the only indication was the position of the manual trim wheel, which was located on the side of the central console. In the heat of the moment, that was not a place the instructor would naturally look. Normally, pilots rely on feeling the forces in the control column to determine the trim position. But now that the instructor had taken over control without a formal handover, he had no such tactile feedback. As soon as he began maneuvering, the first thing he heard was the overspeed alarm, indicating that the aircraft had exceeded the maximum speed for slat set at 15 degrees. The instructor, seeing that the aircraft's flight system was in go-around mode, immediately disconnected the outer throttle and reduced engine thrust, which made sense given the overspeed and acceleration. But this action, while logical, had a disastrous effect. Because the aircraft had been trimmed nose down, reducing thrust from the engines only increased the nose-down tendency caused by the engine's underwing position. When the instructor reduced the thrust, the aircraft's pitch attitude dropped dramatically, from -3 degrees to -7 degrees, and the descent rate skyrocketed to 3,000 feet per minute. The instructor quickly pulled back on the control column to counter the pitch, but to his surprise, the aircraft did not respond as expected. This is where the power of the stabilizer became a critical factor. The stabilizer, especially at high speeds, is much more powerful than the elevators, and the forces acting on it were so great that the instructor couldn't overcome them with the control column alone. The stabilizer's aerodynamic forces were overwhelming, and no matter how hard the instructor pulled back on the controls, the aircraft's nose would not rise. Here's where the key issue lies. The instructor had been trained in a simulator that gave him an unrealistic impression of how the aircraft should behave in this situation. In the simulator, the stabilizer's effect could be overpowered with relatively low force, even at high speeds. This unrealistic training had led the instructor to believe that he could pull the aircraft out of its dive without needing to adjust the trim. However, this was a fatal misconception. In reality, the stabilizer's power at high speeds far exceeds that of the elevators, and the only way to correct the dive was to adjust the trim and reduce the nose-down forces. Unfortunately, the instructor didn't realize this and failed to make the necessary adjustment. This fundamental misunderstanding, born from the simulator's incorrect feedback, was now playing a direct role in the escalating crisis. Pilots are trained to recognize that extreme control forces must be countered by adjusting the stabilizer trim, but the instructor's lack of awareness of the trim position, combined with the incorrect training, led to a critical failure to address the situation properly. As a result, The aircraft continued its violent descent, and the instructor was unable to regain control using the conventional methods he believed would work. This is a tragic example of how even experienced pilots can be misled by inaccurate training and flawed perceptions. The combination of poor communication, unrealistic simulator training, and the overwhelming stress of the situation created a perfect storm. One that could have been avoided had the instructors been fully aware of the aircraft's actual behavior in high-stress, high-speed conditions. This incident serves as a stark reminder of the importance of accurate and comprehensive training that reflects the true dynamics of the aircraft in real-world scenarios. As the aircraft continued its terrifying descent, the tension in the cockpit was palpable. The instructor, despite his years of experience, was still grappling with a combination of misconceptions about trim and the overwhelming physical forces acting on the controls. During the 1980s and 1990s, there had been several incidents involving the Airbus A310 and its predecessor, the A300, where the trim system had contributed to accidents. In these cases, the autopilot would move the trim to its limit, followed by a disconnect, and then the pilots would fail to use enough trim when attempting to recover from the upset. The instructor, having studied these incidents, had formed the belief that overuse of trim was the root cause of these accidents. As a result, he hesitated to adjust the trim, convinced that trimming too much would make the situation worse. Unfortunately, this misconception became one of the two key factors that prevented the aircraft from recovering sooner. It's exactly this kind of misunderstanding that makes studying past accidents so vital in aviation. Understanding the nuances of what went wrong in these situations can prevent future tragedies. At this moment, the situation was critical. The aircraft was descending rapidly, and the only way to arrest the descent was to trim the nose up. But the instructor's reluctance to adjust the trim kept them in a downward spiral, with the instructor straining against the extreme control forces, trying to pull the aircraft up. The captain, likely still affected by the somatogravic illusion, also might have been subconsciously limiting the aircraft's ability to pitch up. This is a phenomenon where the pilot's inner ear misinterprets acceleration as a pitch-up, leading to conflicting inputs between the instructor and the captain. Though we can't know for certain whether the captain was actively pushing the nose down, it is entirely possible that he was, unknowingly adding to the chaos by resisting the climb. As the aircraft descended through 1,800 feet, the tension in the cockpit escalated further. The microphone was accidentally keyed, broadcasting the pilot's panic-stricken dialogue over the air traffic control frequency, a chilling sign of just how desperate the situation had become. Meanwhile, the airspeed continued to climb past 345 knots, triggering the terrifying sound of the overspeed alarm. The Ground Proximity Warning System, GPWS, added to the symphony of alarms, warning of terrain and the need to pull up. The pilots now had mere seconds to correct the situation, or they were going to crash. What neither pilot knew at the time was that despite the chaos, the aircraft had started to offer a narrow window of opportunity to recover. Although the instructor had refused to use the trim for fear of worsening the situation, the flight data recorder revealed that the instructor had inadvertently inputted 6 nose-up trim commands during the dive. These short, unintended inputs, each lasting less than a second, were likely the result of the instructor bumping the trim switches while struggling to pull the aircraft out of its dive. Additionally, the Airbus A310's speed trim system, a function of the flight augmentation computer, was beginning to slowly trim the stabilizer nose up. Speed trim automatically adjusts the trim based on the aircraft's airspeed to improve handling qualities. While this system doesn't work quickly, it only moves the stabilizer at a rate of 1/20th of a degree per second. This gradual movement was also working in the background to help bring the aircraft out of the dive. Together, these two factors, the inadvertent trim inputs and the slow action of the speed trim system, began to have a cumulative effect. By the time the aircraft descended through 2,500 feet, the stabilizer's nose-down trim had reduced from 2.7 degrees to 1.2 degrees, just enough for the instructor to begin pulling the aircraft out of the dive. With immense effort, the instructor continued to pull back on the control column, and slowly but surely, the descent rate began to decrease. At just 995 feet above the ground, the aircraft finally pulled out of its deadly dive. The airspeed, which had peaked at a terrifying 370 knots, well above the aircraft's maximum speed, began to decrease, and the aircraft transitioned into a shallow climb. The recovery, though successful, was incredibly close to being too late. This sequence of events underscores the terrifying complexity of flying an aircraft under extreme stress. Misconceptions about trim, compounded by the instructor's hesitation to use the trim system, nearly led to disaster. But even with all the odds stacked against them, a combination of inadvertent inputs and automatic systems working in the background gave the aircraft just enough of a chance to recover. However, the flight was far from over, and the pilots, now aware of the severity of the situation, still had a long road ahead of them to bring the aircraft back under full control and ensure that they didn't lose this hard-won recovery. This incident, like many others in aviation history, serves as a stark reminder of the importance of understanding and applying systems correctly, even under the most intense pressure. It's also a reminder that in moments of crisis, every second counts, and the smallest of errors or misunderstandings can have devastating consequences. The aircraft, after what seemed like an impossible recovery, was finally climbing back to a safe altitude, and the flight crew could breathe a collective sigh of relief. The forces on the control columns began to decrease as more trim inputs were recorded, allowing the aircraft to regain stability. By the time they climbed through 2,600 feet, they were out of immediate danger. However, the situation was far from resolved. The captain, recognizing the gravity of the situation, made a pan-pan call to air traffic control, signaling a level of urgency, though not quite the distress of a mayday. However, in the chaos of the moment, no one had remembered to switch over to the correct frequency for the terminal controller. The tower controller, who didn't fully understand what a pan-pan call meant, a term rarely used in North America, simply told them to switch frequencies, unaware that the crew was in a highly urgent situation. As they tried to communicate this to the tower controller, confusion mounted. The flight crew failed to dial in the new frequency for the terminal control, and the captain repeated his pan-pan call, now adding that they were experiencing an airspeed indication problem. Eventually, the confusion was sorted out, and the aircraft was established on the correct frequency. The pilots were cleared to climb to a higher altitude and were able to confirm that all their instruments were functioning correctly. While this reassurance allowed the pilots to cancel their emergency call and continue their flight, it was clear that the aftermath of the incident had left them shaken. The flight continued normally after that, and about 45 minutes later, the aircraft safely landed in Montreal, with all passengers disembarking without incident. While the passengers were likely unaware of the intensity of the emergency, it was clear that the cabin crew had experienced some tense moments. On the ground, once the engines had been shut down, the pilots tried to debrief the situation, but they found it nearly impossible to piece together exactly what had gone wrong. Initially, Air Transat suspected wind shear had caused the upset. The Transportation Safety Board of Canada, TSB, didn't consider an investigation necessary at first. But when the flight crew reported an airspeed indication problem, the TSB opened an investigation 14 days after the incident. By then, the cockpit voice recorder, which had only recorded the last 30 minutes of flight, had been overwritten. Fortunately, the flight data recorder was still available, along with the pilot's first-hand accounts, which allowed investigators to piece together the sequence of events. The TSB concluded that the incident resulted from a combination of factors: inadequate preparation for a high-performance takeoff, late rotation, inappropriate use of the trim by both pilots, and a lack of communication between the two, which led to task saturation, loss of situational awareness, and an inappropriate emergency response. These issues were compounded by inaccurate simulator training, which had led to negative training experiences for the pilots. In response to the investigation, Air Transat made improvements to their procedures and training, focusing on low-altitude level-offs, low-visibility takeoffs, autopilot use, and recovery techniques. Quebec City Airport also revised its procedures, no longer issuing departure clearances that required both heading changes and immediate level-offs. Perhaps most significantly, Airbus made corrections to the control force modeling error in their A310 simulators, which had led to negative training for these pilots. These updates were implemented on all A310 simulators worldwide. This incident, while terrifying, was a valuable learning experience that contributed to the continuous improvement of aviation safety. The lessons learned here, particularly the importance of accurate training, communication, and preparation, are a key part of why aviation is as safe as it is today. Despite the terrifying sequence of events, no lives were lost, and the pilots were able to recover the aircraft, showing just how much must go wrong before disaster strikes. And that's why studying these types of incidents is crucial. It's through examining such mistakes and learning from them that the aviation industry becomes stronger and safer, preventing future tragedies. Thank you for following this detailed breakdown. Don't forget to like and subscribe to stay informed on more aviation insights. Have a fantastic day, and I'll see you next time.